Oh man, this is it from the COVID-19 series. RJC Teach. March 18th, 2020. We're still here. Who knows for how much longer. But anyways, this is going to be my final video for now. And I hope you guys have enjoyed these videos and get a lot out of them. There's one thing I haven't mentioned when it comes to relative dating that's super, ultra, amazingly, absolutely, tremendously important. And that's a thing called an index fossil. Okay, and why is an index fossil unlike any other fossil? Well, you guys got a bunch of things called index fossils all down here, including the New York State Index official fossil of New York State called the Eurypterus. Looks like a lobster guy. I've been out on many hunts for him in the fossil bedrock, have never found a Eurypterus. Okay, I found lots of pieces of, well, not even pieces of Eurypterus, lots of pieces of other things, crinoids, trilobites, bryozoans, plesiopods, but never Eurypterus. So I'm still on the prowl. They have some amazing fossils in the Buffalo Museum of Science. Now, you see how he's got a letter M? Now you guys are going to go to this on page 8 and 9. You better pay attention. You guys you have to know this. Oh my gosh, you have to know this. Okay, where's letter M? He's right there. This means we don't find any Eurypterus in the fossil record, any kind, until Ordovician period of time, more than 444 million years ago. Now, we find them in the fossil record, and then we no longer find them. You know what that means? That means they became extinct. Ex-nay, no longer around, due to cataclysmic change on Earth, gradual changes, whatever. Trilobites. We see trilobites like letter A. What is letter A called? Letter A is over here. It's called elliptocephala. What does it mean? Fathead. It means fathead trilobites. We find those, and those are a marker for the Cambrian period. We find Crystolithus is what they changed into. We find Crystolithus dominating the Ordovician. And we find the ones that we find around here called Phacops as dominating what's called Devonian. Well, here's the situation, people. These are time markers. The only time Phacops fossil kind of trilobites were around was the Devonian period of time. So if you find one of those anywhere in the world, the rock is Devonian age. That's cool stuff. If you find a fossil of Eurypterus anywhere in the world, you could say that that bedrock was laid down at the same time as the bedrocks formed by ancient seas in New York State. Because letter M is a marker for the Silurian, no other time periods. So what makes a good index fossil? 2 rules. Short-lived existence, relatively speaking, like one period of time, which isn't so short really, and found all over the world, widespread. Short-lived, widespread makes you a good index fossil. Generally speaking, on our diagrams, which are oversimplified, one rock layer, every rock sequence that we can find. One rock layer in each sequence. Let's say there's 4 different places in the world, all in one rock layer for that fossil. It would be a good index fossil. Another thing that's really a good index time marker is ash, volcanic ash. Because when a volcano blows off, it covers a big area in a very short period of time. Everything above it younger, everything below it older. So these are time markers. Short-lived, widespread. Their letter marks the period of existence when they were around, the one that they mark. And you can also see when they came around and when they also died off. And you can also see that some organisms like crinoids are alive and well today. Now we got one more thing to talk about. This is called, what we just have gone over is relative dating. We also have something called absolute dating. Now absolute dating actually has to do with page 1, wait right there, of your reference table. And on page 1 of your reference table, you actually have this. You actually have a radioactive decay chart. And it shows what the material element starts at and what it decays into. Now, we actually already know about this decay. We know that if a dog poops on your lawn, eventually that poop will decay and become fertilizer. This is the living matter, or exiting matter, and this is what it decays into, nitrogen fertilizer. Carbon changed into nitrogen. In a greater sense, uranium changed into lead. Now here's the deal. Those rates of decay are broken up into what's called half-lives, and nothing nothing on the planet, not atomic warfare, not moving rocks around with plate tectonics, not really, really big people stepping on them, nothing changes the half-life of these materials. So how does this work? Here's a simplified version of how this works. So here's a bone that I discovered in my backyard. There's a bone that I discovered. I got to it before Fido bit it. Now, if this bone was present-day age, everything that's present-day age is made up of, if it was once living matter, it's made up of carbon. We are carbon-based units. All bone structures, all tissues are made up of carbon. We absorb this carbon from the air. It's part of our makeup. The second we die, our carbon starts to decay into fertilizer. We essentially become fertilizer. We change into nitrogen. So, if I study this bone and I know that it has all whole carbon-14 atoms, in fact, for its size, it has all the carbon-14 that it should have. It's called present-day age. It's not old. However, if I study this bone and I find that half of its carbon-14 is turned into nitrogen, in fact, let's make a key. This will be carbon, and this will be nitrogen. I'm just going to run out of room. You're going to have to take my word for it. That says nitrogen. If half of it is present, how many half-lives have gone by? One half-life. Half of the carbon after death has started to decay. It turns into nitrogen. How long does that take? It takes 5,700 years for that to occur. So, how old would that fossil be if it has only half the carbon-14 in it that it should, and the other half is turned into nitrogen? It would be 5,700 years old. But let's say when I did study this with an X-ray refractometer at the University of Buffalo, we were able to decipher that it doesn't contain half nitrogen. This material, this bone, contains 3/4 nitrogen and only 1/4 the carbon that it should. That means one half-life has gone by, two half-lives have gone by. What's 2 times 5,700? If all you have is 1/4 of the carbon-14 left, you have 11,400 years old. And it would continue. 1 half-life, 2 half-lives, 3 half-lives would be 5,700 times 3, and you only have 1/8 left. 1/16 left. The bottom line is, if I cut that thing up like 7 times, I no longer have any carbon-14 left to even measure. 7 times 5,700 is about 40,000 years old. After about 40,000 years old for fossils, I gotta use something else with a longer half-life. Carbon-14 is awesome, awesome, awesome for dating the ages of early man, dating the ages of ice age creatures. But you start to get like dinosaurs and trilobites and something like that, we have to use something that's much a longer half-life, like uranium. In fact, uranium is awesome because one half-life is 4.5 billion years. And the oldest rocks on the planet, incidentally, have about half the uranium that they should. The uranium has been changed, decayed to lead. And that's why we believe the Earth is about 4.5 billion years old. See, this isn't a relative dating thing. This is an absolute dating thing based on radioactive decay. Guys, it has been awesome. I hope you enjoyed the videos. I hope you benefited from them. Share them with your friends. Have a good laugh. Break out the popcorn. Throw tomatoes at the TV screen as long as your parents don't get upset. And be safe. Hopefully I'll see you soon.